samples. First, we tried the zircon because it was the one that we thought that it would be easier to get. And we tuned it for different pHs. It shows better results at lower pH. We got really pure zircon in here, although it shows some anisotropy on the growth when it's formed. And we tried it at 100, 150, and 200 degrees. At 100, we only obtained the oxide, zirconium oxide, and silica. And at 200, we obtained the zircon pure as well, but we preferred lower temperatures for the synthesis. So now we changed to the cerium silicate that is called stentitite, and we tuned the pH in the same way. Stentitite seems to like, on the other hand, a higher pH, and it doesn't show that anisotropic behavior on the peaks. As for stentitite and zircon, the pH seems to be different, the pH of formation. We decided to get into the middle point, that would be 0.75 sodium hydroxide, that it would be around pH 1 for the mix. And we decided to try to obtain what are the mixed silicates from zirconium and cerium. What we got is that using temperature of 150 degrees and the sodium hydroxide concentration that I mentioned, we could obtain the pure phases as it happened before. So it's a reproducible process for all of them, but we didn't manage to obtain the intermediate phases, in what we will obtain or the oxides, as in this case, or we will obtain oxides plus the pure silicates into the same sample. So a heterogeneous sample in here. So now, once we have the non-radioactive, well, first we performed the IR as well to know what are the environment of these silicates. It shows that for zircon, there's some kind of hydroxyl water present in this structure, while in stentitite there's not. It has been reported that it's quite probable from the tunnels that zircon has in its structure in the 001 direction, whereas I would expect that zircon has a lower ionic radio.
Your 15 minutes is here, so I'm just alerting you.
Okay. Zircon it will have water in the structure. So we saw the anisotropic behavior in here, the same for zircon that will grow these kind of particles, and for stentitite that it doesn't show it by spherical particles in this case. We tried it with thorite that we could obtain the pure phase. Basically, we used the same conditions, but we did the reaction for 24 hours and 250 degrees, and we obtained the pure sample. And for coffinite, we haven't managed to obtain the pure sample yet, but we obtained this black sample that would be some kind of uranium oxide plus this yellow one that would be silica and the oxide. So we expect we need to change the concentration of the precursors, plus making more attempts on these uranium silicates. So as the future work, currently we are changing the concentration to see what is the optimal concentration for the synthesis. We are sending these thorite pure samples to the synchrotron network measurements to UK at the moment, so they can test it at really high pressures. And we will try to make the coffinite using a different uranium source, in this case uranium-3, although it's really difficult to obtain it stable, so it's been quite challenging now. Obviously making the intermediate spaces for the mixed silicates, and we are trying currently the different silicates like lead silicate that it doesn't occur in nature or synthetically, but the preliminary results are quite promising, and similar compounds like cuprochloroscite, to see if this technique can be extended to some other silicates. Finally, thank you all for attending. For my group, especially for Peter, and Andrew that got his PhD recently, and Annie for the lovely images, and obviously to our the the people we've been working with from the Bakers Group, Bob Baker and Sam. Looking forward to your questions.
Thank you so much. I don't see any questions posted on the chat site, so I'm going to ask you a question or two. The first one, I saw from your synthesis that you start from a sodium salt. Do you end up, but you seem to have very clean products. So how do you avoid something like what happens in zeolites, where you can get mixed metal outcomes? Or do you actually have situations where you could get different structures with sodium cations as well as +4 cations?
From what we've seen, in all of the cases, we don't obtain any mixed one. And the sodium is actually present as sodium chloride in the sample. So after we synthesize it, we centrifuge it and we wash it with water. And all the sodium is basically gone by then. Okay.
And there's a question also from Professor Cole Hamilton. Why do you think the uranium does not end up incorporating into the products?
Well, there are few. We think that it could be because the concentration is not high enough. We've been following the rules for the risk assessment, but we would need to tune it for a higher concentration at this very moment. So it preferably makes the oxide in that concentration, and as well, it seems the oxidation state is not stable as uranium-4 in our reaction conditions. So it's making uranium-6 straight away.
Okay, and last, before we move to the next speaker, a question from Vasily Lebedev. Do you think you can scale up
for 24 hours and 250 degrees, and we obtain the pure sample?
To a scale that would be
and
needed
for coffee
if
nights,
you did succeed in making
we haven't
uranium salts?
To obtain the pure
sample.
Scalable would mean higher concentrations, which wouldn't be a problem in this case because we tried higher concentration and the concentration being higher is not a problem, it's just being lower. And as well, it's a really simple technique. It just needs water in a sealed container. It's already used in industry and this kind of reactions. So it would be some kind of uranium oxide.
Okay. Thank you again, once again. And normally we would appreciate it with a round of applause, but you get a virtual round.
This yellow one, that would be silica.
We will now move to the third speaker. And I don't know if you're Kelly Connor or Connor Kelly. I guess it could be either way around, right? But,
yeah, it's Connor.
So I will go with Connor. You're from UCD, and you'll be talking about the trigonal prism.
We need to change the concentration of the
for manganese
precursors.
Perfect. So I hope you can see my screen okay.
No problem.